Here we are in lecture sections 14. In the 10th edition, we're talking about files. And we figured out last time that this LA, which has a logical address, is really basically a physical address. And if you divide it by the size of each of these boxes, you'll get the quotient will be which box it is. For example, if it's 4, the quotient will be 0, so it's the first box. And the remainder will be 4, so it'll be the fourth offset in it. But that's not really the main thing that I want you to get out of this. The main thing I want you to get out of this is that these files are contiguous. In other words, well, this could be a logical address. Maybe that's also what they're saying. Let's think about. I think I can explain why it is a logical address. Because, for example, if I know that 14 is at 14, because it tells me that TR is at 14. Yeah, that's so we have to take the starting address. That's what it is. Block to be accessed is the starting address, which is 14, plus the Q. So it is the logical address. You see what I'm saying? In other words, I just know that I want to go to the 513th block, 513th byte in my program. I go to the directory table and it tells me, well, your starting point is 14. So where is 513 going to be? 513 is going to be 513 divided by 512, which is 1. So it's going to be 1 plus starting address. Q plus starting address, which is 15. That's 14 plus 1 is 15. So now I know. And then where is it? If it's 513, it's R would be also 1. So it would be the first one in 15. So it is a logical address. Now there's a logical but it's a logical address where we're also using this directory structure here.
What is RB2, not 1?
So therefore, wait a second. Therefore, since it's contiguous, this works. This only works because it's contiguous, right? Because if it wouldn't be contiguous, then there's no guarantee that the next byte, if I get a Q of 1, who says that this 15 is really the next one? If it's all scattered around the machine. So it only works because it's contiguous. Question.
If we say 513, would RB2 not 1? Because it's
No, it'd be 1.
From 0 to 511?
It'd be 1.
Okay.
If it would be 512, it would be 0. The remainder would be 0.
Okay, fine. Yeah.
512 would also be Q of 1.
Yes,
But it'd be the 0.
Fine.
I just like to pick 513 so it's clear. Okay.
Clearly more dependent.
Well, I just want to be sure that I'm more at 512. But yeah, 512 also divided by 512 is actually 1.
Yes.
So therefore the Q would be 1.
The
And it would still be that same 15, but same 15.
Yeah.
So that's what it is. So we have to, this is just giving us the offset from 14, for example, for TR. Okay. Anyway, this is a system.
So the 512 is the size of the block.
Yes, block size. See, it says block size. So now this makes sense. Everything here makes sense and is in place. Okay. Now this is that was contiguous. Many newer file systems, I have no idea what Veritas file system is, use a modified contiguous allocation scheme. How is it modified? Extent-based file system allocate disk blocks in extents. An extent is a contiguous block of disks. Extents are allocated for file allocation. File consists of 1 or more extents. In other words, that's the key point. The key point is here. The file consists of 1 or more extents. In other words, it can be distributed, but each section is contiguous. So you could have a combination of contiguous and not contiguous.
Why are there blocks of disks? Multiple disks?
Yeah. Yeah. We don't have to know this for the example. Okay. Now I guess I'll skip that. This you do have to know, linked allocation. So here's a picture of it. I'll jump to the picture, we'll go back. But here you see we have a start. It tells you the start and the end. And then how do you get to the second one?
You go to
Well, the start, it's not contiguous. From 9, we're not gonna go to 10. From 9, we're going to 16. How are we gonna know that? Well, in the block, there'll be some kind of reference, kind of like linked list that you did in data structures, where in each node there's a pointer to the next node. So this node, this 9, some of its data will be used up on pointing to the next node. So let's see, let's see how we describe it. Each file is a linked list of blocks. File ends with a nil pointer, right? The last one has a pointer to no number, or to -1. Of course, then we don't really need this end here technically.
And I think that,
Unless you do
and
that.
the end is probably make it faster for each end of the file out, so.
If you wanted to append to the file, right, it might be helpful.
Oh, yeah, that's why you
Instead of like going through the whole list.
Yeah, but that's only like in one special case, okay.
But it's also if you want to read the file setting to end or something. like,
It's mostly for appending. Okay, file ends with a nil pointer, no external fragmentation. What do we mean by that? In other words, we don't, if it's contiguous, we might have gaps, we might have a block that we couldn't allocate, but because here we can spread it around, we can use every single block. Of course, there could be internal fragmentation. Each block contains a pointer to the next block. You understand why there's no external? External means that there's space that's unassigned and it can't be assigned because it's too small. No compaction is necessary. And no external fragmentation. We've said that already.
Yeah.
These slides are not, I have not edited these slides. Free space management system called when a new block is needed. So. We have to have a management system to keep track of all the free space, obviously.
Yeah.
But wait, say when a new block is needed, if I want to expand the size of the file, it's actually quite easy. I just find a new block. Whereas in the contiguous, it's much harder. I'd have to move the whole file. Right? I'd have to move the whole file to a new place that accepted a larger space. Improved efficiency by clustering blocks into groups. But increases internal fragmentation.
Because you could delete something in the middle, and then you still have to.
Now, we could have a group of blocks. We could have like, this one that uses 15, 16, 17, and then 25, and then 2. In other words, put those 15, 16, 17 all in a row. We could try to improve efficiency like that. Like, if the pointer, we could have a special rule that if, I don't know, we
I
assume
think
that
it
the.
automatically does it, it's like caching, it's like locality.
Well, anyway, the disk will have to move less if the next one is adjacent, like the head will have to move less. Reliability can be a problem. Why is reliability a problem?
Something gets corrupted.
Right, you can
One
lose, you
link.
could lose, if you lose one link, you lost the whole file. One link goes,
Anything after it.
everything after is gone.
That's pretty bad. Why does it say that clustering blocks increases internal fragmentation
Where does it say that?
in that line?
Oh.
Interesting, because you could like put them all together so that it's like as if we had.
Oh, no, I know what it means. What it means is like this, instead of having a block, good question, now I have to explain it better. What it means by clustering blocks, like I said, 15, 16, 17, and then, that's not what it means. What it means, really, I said that wrong. What it means is, we could say there's a cluster, we'll invent a new word called a cluster. And the cluster will be 4 blocks. We're gonna still use the concept of blocks, but now we're gonna assign people only by clusters. So you can have cluster here, cluster, so the links will only be 1 per cluster, and each cluster will have a fixed size. So you can say, we'll just call that the block size. Well, the block size is still gonna be relevant for other factors, like maybe copying a block, maybe you have a DMA that copies blocks or
And
something.
you got a variable cluster size.
You could theoretically, of course, everything is possible theoretically.
Yeah.
Yeah, anything is possible, but there is a concept in operating system called, or in disk management, called a cluster. And a cluster is a group of blocks, and let's imagine it, I'm gonna imagine it always as a fixed size.
So this is kind of like a combination of contiguous and linked allocation.
Yeah, but it's
Cluster somewhere.
it's really just linked with where the blocks are bigger, instead of being block size, they're a new size called a cluster. Okay, so therefore we have larger internal fragmentation because you can't assign a half a cluster, you can only assign a whole cluster. Locating a block can take many IOs and disk seeks, right? We have to run all around up and down to find all the pieces.
Yeah.
So here's the example we saw already. Now, how are we gonna map? So we're gonna still take, so we have a start, but we're gonna take our number, and what does it say? Block to be accessed is the qth block in the linked chain. So Q actually does tell us how many jumps we're gonna have to make. Which is actually, in other words, we need to know how many jumps to make. You need to know which node is where you're looking for. So you take a logical address, let's say why 51?
It's 500, like Mine's.
Why-
Oh,
why-
511. Well, why 511, not 512?
Because zero is the pointer, the start.
Is it- No.
But
no,
the
it's
first
like-
one is
Offset is still 512. You can't.
You
change
can't
the
access
offsets.
the first. I'm saying you can't change the first,
But I mean,
because I want to delete the
you
first,
can't jump
Because,
around.
no, because we want one. If it's five,
like jump one. Like jump
if
zero.
it's, if it's like the number five, then we're gonna have one jump, right? Because five is less than 512, so the Q will be 0, so it'll be in the first one. And if it's 511. Why would we still be in the first one? Oh, I'll tell you why. I'll tell you why. Think about why, if it's 511, address 511, will we actually go to the next one? Think about it.
Because it's the number of jumps, it's the number of next.
No, it should still be the first one.
No, it's a
There's
zero.
512 bytes in that one. Why would I, for 511, it'll be the last one, I should be able to get there.
Last one. You do get to.
From 0 to 511. But if I would write 511 as LA in this case, then it would be 1, which means go to 1 jump, not the 0th jump. Not 0 jumps. Just go to the second node.
511 wouldn't give you a remainder of zero.
No, 511 divided by 511 is 1. Q is 1.
Oh,
And
okay.
Q is how many jumps to make. And I would make 1 jump. Why?
I
It's a very simple
I
answer.
think Shai said it earlier.
Why?
There's a place for the pointer.
Yes.
Shai said it.
So I
At the
said
very start.
Why you forgot? You forgot what you said that?
Huh? Well, I thought maybe that you could do
I
it a
didn't
little
hear
bit
you.
differently.
It is not a while ago.
Yes, exactly. There's a byte for the.
It's the first one.
For the,
Yeah.
not for the first one.
I'm saying that it's the pointer, like the beginning.
There's really only 511 bytes for you.
Yeah.
So that's why it's 511, because there's always at least 1 taken up for a pointer. Maybe it's 2, but depending on the system, right? It could theoretically be any amount, but that's the idea of 511. That's what you meant, yeah.
I mean, kind of, I thought of it a little bit differently, but.
But basically, there's only 511 actual usable spaces. So if you give me 512, it's not gonna be in the first one, it's gonna have to be in the second one.
And then it also says R plus 1, because you jump up with the.
Displacement into block R plus 1, because. Why? Because,
You
why?
want to jump after the pointer.
Well, let's say it's 511. So what's R?
1.
0.
0 plus 1.
Why would we have to
Because
go?
you don't want to access the pointer, you want to access the first part of the block.
Oh, there's a point at the beginning of the block?
Yeah, I think it was.
That's what I was
Oh.
assuming. That's what- yeah, I don't know. what-
Ah, okay. I was thinking the pointer is at the end of the block.
I guess it doesn't really matter.
Yeah,
It doesn't really matter.
Here they're saying it.
Fine.
That makes calculation easier because you can do R plus 1,
Yeah.
otherwise it's just a weird.
So what would be
Otherwise-
the first block? The block is just
You know,
all
otherwise,
pointers?
otherwise, no, otherwise it'll be fine, it'll change our.
Right, you would have changed
Yeah,
R.
so I don't know, that's your way is better, I change all that.
Yeah. You're gonna change, you're right. If it would be my way to the end, then it's just whatever the remainder is. It'll be-
So what part is that then? The
But what about the second one? What about if the number would be 500, 1022?
Oh, okay.
Yeah, okay,
Yeah,
so it'll still be. Okay, I guess it's still, okay, so this is this idea of linked, and this is this nice LAQ. Ooh, I think I'm more better than asked about that, but I don't think I asked about this in my goal. Okay,
Did you ask why 512?
no, uh,
Hopefully none of us will see one.
file allocation table, so this is my favorite one because. I heard of it before I ever started teaching this course, because this was one that was very popular in the 90s, let's say. And it's called FAT, it's an easy name to remember, FAT, file allocation table.
Didn't
And-
we have a thought earlier? Yes.
In this
This what?
in this context, I'm saying we had it in this
Ah, it
context.
was also called thought.
This is,
It's in,
we learned it already?
we just mentioned it
We
as
mentioned it,
a,
So
as a
here,
format for.
yeah, so here's what you do.
Yeah.
You have basically, this thing is, you see, notice that this is a cylinder here?
Yeah.
This is not a cylinder because we didn't, for some reason, they didn't draw the cylinder on the page here, they should have, because it's confusing. But in addition, imagine there's a cylinder over here. And then in addition to the cylinder, we have this thing, which is a file allocation table, which is in memory, basically, or it could be on the disk, it has to be on the disk, when we turn the computer off, it has to stay around. So it'll have to be on the disk, but eventually it'll go into memory, let's say, it'll be copied into memory. But we'll have a but it'll have to be, and what is the file allocation table? What it does is like this, very clever idea. You have one file allocation table for the whole disk. And what you do is you have directory entries, which say the name of the file and blah, 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 whatever other information, and also the starting block. So we only keep track of where the block starts, and that's, and just like we did before. Just like we did before, we have a start.
Yeah.
And just like we did in the other example, we have a start. We always have a start. So here we have a start. But the start, and so the start tells us go to file allocation, and this tells us where the first block is. So now we know already where the first block is. We don't have to use the file allocation table to get to the first block. We want to just read the first byte of the file. We already have the number. We use this file, this 212. We go to the disk, we go to the cylinder, and we read that block. What if we need the second one? So we go to 500, 200, we go to index, we go down this table to the 217th row.
Of the same fat table,
We have one fat table.
and it goes to itself.
Wait. Just let me explain it. I'm in the middle of a sentence. We go to row number 212. Notice these row numbers going up. We go to row number 217. And at that row number, we see the number 618. And what does 618 mean? It means that's where that is the value of the next, in other words, on the disk, 618 is your next allocated block. And also, and if I want to know where the next one is, well, I simply go to 618 in this row. And now I jump down and I see that it's 335, 339. So 339 is my third disk. Is my third block. So in other words, there can't be anybody else using 618. Since I'm using 618, then this row has to be for me. Now, how will I know when I'm finished? Well, pretty simple. When I go, if I want to know where the end is, I can just say when I get to this one is 339. First of all, I know to read. Now I jump over here and I read in the disk 339. Now I want to know if there's another one. So I go to place 339 and I see nothing there, or I see a -1 or 0. Probably -1. I see some indicator that says this is not a valid place, and I know that I've reached the end. So it's pretty reasonable. That's a pretty good system. Now, what is this number of disk blocks?
Show you that.
Oh, I understand. There should be no space here. Number of disk blocks -1. In other words, if you
It's the second last one, that's correct.
yeah, it's just saying that like this is the last block. If there's 500 blocks, then this is block number 499 because we started at 0. It's just that little space here.
Sorry.
Okay.
It's
like-
like an arrow between the -1 and
Because
the
it's
line.
not, that -1 looks like, no, there's,
Looks
the
like a-
value of this last row is going to be. Whatever, 1,000 or whatever number of disk blocks -1.
So is that faster?
Oh, so is it faster?
Seems like a lot more accesses.
Well, explain, yeah, so this is a great question for the exam. What is the advantage of this system versus
Because
this system?
this one is in memory, another one is on the disk.
If you
Exactly.
link,
This one, in order to get to the next block, I gotta spin the disk around and actually load from the disk this block. Here, I have it, I just load this is all fitted into one block. And I load this one block into memory, and I've got now access to all my files, every single file. What's the disadvantage of the system?
Takes a lot of space in memory.
Yes, flashes.
Okay, it could take a lot of space in memory.
It's slower if you're going to like the next, going to the 5th block. You can just do 5 different operations to find where the 5th one is, so you have to jump around.
No, this is slower. In order to get the 5th block, I have to jump and jump and have to read all these blocks. to
No.
get-
Saying if you wanna do if you wanna get that.
By the way, why is it that the pointer is at the beginning of the block? Should be at the beginning of the block. Can you tell me why now? Just think about it. Why should it be at the beginning? Remember I said? I thought it was at the end?
Because a platter is spinning and going to,
Because the first thing I do is I jump to the block and I'm at the beginning of the block. So I wonder if I don't want to be at this block, I just want to get to the next one. Then I just want to read one byte. I don't want to have to get to the end of it. In other words, each time I jump, I get to the beginning of the block. So if right there is the pointer, then I have the pointer in my hand and I can now jump to the next one. If I want to do 25 jumps, I don't want to have to spin through the whole I don't want to have to. Exactly, spin through the whole block in order to get to
The
the,
hardware things are usually
But
done
it's also-
with loading blocks, right?
what?
Aren't hardware things usually done with loading blocks, not loading single bytes?
Yeah, but still, yeah, you're right,
Also,
maybe,
you do that to
maybe
edge,
it's a
that's
small
the change.
advantage, but I think that might be
It
the,
isn't.
I think that must be the advantage.
If you wanna.
Anyway,
append
but
to
what's
the
the
file-
disadvantage? The advantage of this is fast, it's for sure faster. In every way, this will be faster, because jumping from here to here, I know exactly where to go, but I know how, I know that I'm on. I know that I'm on 217 and I know I need to be there, I just tracked and I know exactly how far to jump, and I go there directly and I'm there, and it's all in memory, this is not on the disk, so it's gonna be the fastest possible jump. I mean, it's certainly less speedy than contiguous, that's for sure. But I didn't ask that, I asked why is it, what's the disadvantage, so that's the advantage, what's the disadvantage of this?
Probably harder to manage.
This is gonna be hard to guess, this one, so I'll tell you. The disadvantage is that the fat is usually stored, is like, let's say, stored in the first block of the disk. If that block gets corrupted, then you lose your fat table, then you lost all your files on the whole computer.
Uh-huh.
And as if the disk got corrupted at that spot, you have no recovery. So what's the solution? You could have duplicate fat tables. Right, you could, anytime you change something, you change it 2 places. But I'm just saying, the problem with the fat is you put all your eggs in one basket, you put everything, here, your risk is a little bit distributed. In other words,
It's even more, I mean, or similar, if you have a
I mean,
corruption.
if you lose the
in one of the
directory.
links,
No, but you don't, so if you have a corruption in a link, you lose that part of the file, you lose a file.
you can't-
Here, if I lose this block, I lost not just one file, but every file.
Oh, yeah. That's
Which is-
that's worse.
Yeah, if your fat table, I remember this as a thing, that your fat table got corrupted and then that's it, it's just fine,
Really?
you'll never find it.
You could combine both methods, right? Like use this for faster and use the linked lists for recovery.
Yeah, then if you ever lose your if you ever lose your fat table, you
Good
just
try, yeah.
build it.
The question I still don't, I have, I should really look up, but I don't really quite understand about the directory entry. Where is that stored? It's also gotta be stored on the disk, otherwise it'd be lost.
Why would it be memory?
Well, it's in memory when you're running, but
Yeah.
when you turn off the computer, you gotta read it from
That's
something.
from the disk. So
It's
this
from
is
the
part of
disk.
fat tables.
So where's the,
Part of the fat tables.
Well, no, we had this even when we didn't have a fat table, so here we have a directory, we still have to have a direct,
Yeah,
we still have to have a directory somewhere on disk, that could also get corrupted.
Yeah.
And then we have that same problem, so here we have it twice, we have the directory can get corrupted and this can get corrupted. Right, if we lose a directory structure, we also,
no, but the directory, in fact, the directory entry is part of the fat. Yes.
no, your directory is only as long as the number of files.
Isn't everything here? Oh, never mind.
no, I gotta know where the start of the file is, the
Yeah.
directory is just telling me the name of the file
Yeah,
and the start. I gotta get the start,
I
without the start, I'm lost.
I misunderstood the picture. It looks like the arrows meaning that it's inside that.
No,
slot.
no, it's not inside.
Question, if you put the pointer hypothetically at the end of a linked list and you wanted to append to the file, would you have to then like have a complicated, go to the
Are you
end
talking
and
about
then
this
go back one, yeah.
Well, we have our end here.
Right, I'm saying if your pointer was actually at the end,
I wouldn't. You can't.
Oh, and it could be nothing in, it could be only 1 byte there, we have to go back up, yeah. Right, yeah, okay, whatever, anyway, continue.
is that the same problem with that?
What is this, what's written here? I'm gonna skip this one. Here, index alloc, it's the same thing, index allocation. Each file has its own index blocks, here, let's just look here. So. This one is also a good system. We keep getting kind of better, really. This one is saying like this, we always have our directory structure. And it tells us 19, and that means that that's the first block. But this block, I think we talked about this. This block is just a list of, I thought we did this before. This block is just, oh, maybe we did a lab? Oh, yeah, maybe we did a
I
lab.
think the lab we talked about this.
Maybe in the lab. we
It's the
talked
same
about
thing as an inode.
this is
Yeah.
basically an inode, yes, this is basically an inode, because we're basically saying. Where we have a single block that takes care, that tells me where all the other blocks are. So. This is like a fact table. But for each one. In other words, for each file has its own fact table. It's like a fact table, but not a universal fact table, but it's a fact table for each. File, and we just need to know the beginning, and then we get there, and then this block tells us where to go, so if we want to get to the 4th block, we just can immediately go to 10. We can just, go, this is index, so we can just go to row 10, row 4, or row 3, and we know 10, and we jump to 10, and that's our complete. And then if we And the -1 indicates to us that there is no allocation. So the problem with this, what's the problem? What's the advantage, disadvantage?
Internal fragmentation is disadvantage.
Like overhead, I think. for the-
We'll have some internal fragmentation because why? Give me a case. Let's say you have a file of 1 byte, how much space will it take up?
It'll take up that whole block, to give, the
Like
next
two
block will
blocks.
take up an entire block. When
1
you-
block?
2 blocks,
Why 2 blocks?
1 block for the index table, and 1 block for the 1 bytes.
Oh, right, right,
2 blocks. A 1 byte file will take up 2 entire blocks.
I was just referring to the index block.
No,
Just
the
the
index block, yeah, and 1 more, so it'll be 2. I think I don't know if I put it on an exam question once in the past, but I asked a question like, I invented a new system where half of the block is used for data. Yeah, so then if it's a 1 byte file, it would still be 1 block. You know what I mean?
Okay, you're just making the blocks smaller, okay.
Yeah, but essentially just making the block smaller.
I guess that's also it's kind of like clustering. Because it's
Yeah.
like a link, but you know where the next one is half the time.
They get smaller.
You easily know where the next block, the next address is half. 50% of the
Whatever,
time.
you could just use some of the space, but then you could change it as the file got bigger. You could kick it out. In other words, once you've used up all the space, then if you still needed more. Then you would find a new block. And put the beginning of the file there and continue using this one.
Oh, so it's not like the beginning, it's like.
No,
you
the
always
beginning of
use
the file.
half- You always use half of it.
Well, you'll waste a half. If you think about it. This system, what I'm describing now would mean that if up till a half of a block, it would be fit in 1 block. Once it's bigger than a half of a block. No, once it's something, it'll go to another block. But once, let's say I have 25 pointers available in my block. Once I've used all 25 pointers, I need another 25. I simply take the data out of the block. And put it in and find a spare empty block, copy it over there, and call that the beginning. And now I have 25 more spaces to use. You understand?
But isn't that like freeing up the beginning?
Yeah, I can always move the beginning where I can.
That's a lot of transferring,
No.
copying from one to the.
No, it's just this number, it means all these numbers I push down 1, and at the top I put in the location of the first block.
It's interesting.
Or I don't even push it down, because the first row will be a -1. And if the first row is a -1, it means that it's here. You know what I mean, that the first block is
And
here.
not jump.
And
back.
whenever I'm displacing it and putting it into a new block, then I'll change the -1 to where it actually is going. So I wouldn't have to move anything.
But what if you're?
I wouldn't even have to move anything, I just change the number from -1 to where it really is now. And so this would get rid of that worst case scenario of a 1 block file, or 1 byte file.
Technically, but.
But it would leave me, when I copied the first block, it would mean that I put it into a space. That was I would only use half of it, the space would be twice as big as what I need. Because by definition, it only took up half of the original first block, and so now when I copy it to a new block, it's also gonna take only half. So I'm gonna have internal fragmentation of a minimum of a half a block.
I guess if you were like.
But in a case like that, the file's gonna have to be very large, if I had to do that. And if the file's very large, I don't mind internal fragmentation of a half a block.
But if you have like, if let's say you're doing something sequentially, you're.
I didn't go into so much detail on these exams.
It's just like half block.
I just said a general idea. I just said, if you use half of it, what advantages, what disadvantages?
If you had your half block filing system and the first one is a negative, the first the first byte in your block is a negative 1, you're like, okay, I'm using this block.
Yeah.
And I used up the entire block, like 1 before the entire block. and
No, I
then-
will never use up the entire block. And also
Let's say the half.
I'll only use up half, and I'll
Then
keep half for
the amount that
pointers.
you would use.
Yeah,
Then when you finish, you go back to the beginning.
no,
But
that's no,
change
once
the-
I've used up half and I wanna add 1 more byte. Then I have to allocate a new block. And I'll put one of my pointers will be pointing to it. After the -1,
The first one.
the first one will be -1 still.
Oh, it's the same byte.
It'll stay -1 because it's indicating that some data is here. When I remove the data from here. And it's empty. Then I change the -1, but as long as there's some of the data is here, I'm gonna keep going.
And how do you know if you've hit the end?
The only time I'm gonna remove data from here. Is when I've run out of pointers, which means the file is very large. Now, it's interesting, it doesn't really gain anything.
You have to like jump back and forth.
I mean, I'm not gonna come up with something that really is an advantage, it's just different way of doing it.
There could be an application to that.
There could be, I mean, it would be
Could be a
advantageous when you,
specialized-
if you expect to have a lot of small files, it would be advantageous.
Maybe for transferring data,
It could be.
you're always going to send it.
If you had a lot of small files, if you had a system that expected that, then it could be a good way to do it. If. Right, what would the worst case, in my system, what would the worst case internal fragmentation be? Total,
Not if you fill the block and then allocate a new block.
Half of the system,
not half of the system.
if each
No,
file is
if-
a block. Then you're wasting half a block.
No, what are you talking about? I don't mean, no, for a given file, I mean for a given file,
For a given file, half full.
no. Think about it.
If you delete parts, what about?
What's the worst case, it's a trick question here, what's the, not trick question, but you have to think a little bit, what's the worst case, for the system I just described, what would be the worst case?
Worst case scenario?
Scenario of internal fragmentation for a single file? It would be the half a block that when I was Mifune, but it would also be the last block of the file could have just one byte in it. So the worst case would be, the last
Okay.
block of the file could always just have one byte in it.
One and a half blocks.
So it'll be essentially 1.5 blocks, or more or less, like -1. The worst case would be 1.5 blocks. Whereas the worst case in this system,
That's two.
no, it'll be 1 block,
And in this one, why?
1 block.
This is what we're talking about right now.
In this system, the one here on the board, the worst case scenario is 1 block.
No, if you have one byte, and you have the index block, which is one block.
Yeah, that's like I'm not counting, that's, we always have to have that. I'm not counting that,
That's fine.
in mine, then there'll be 2.5. You're not counting, that's overhead, that's not internal fragmentation.
Yes, fine.
Okay, anyway, let's go on. So how are we gonna deal with getting our address? We have our LA minus 512 again, divided by 512. Need index, wait, so we need this index, right? So need index table, so that's what I think it's referring to this thing.
Yeah.
Random access, oh, that's an advantage, it allows us random access because I can just jump to any one at any time, I don't have to hop and skip through the file. Dynamic access without external fragmentation. But have overhead of index block. What do you mean dynamic access? What's the difference between random access and dynamic access? Why is it no external fragmentation? Like use any block.
What's it done now?
Dynamic, I think it means the same thing as. I don't know what. I mean, unless you mean to say that I can add. A block, maybe that's what they mean. Dynamic usually means while the program's running.
Yeah.
So I could add a block while it's running, right? Because. If I add a block. I just put another number here. I can dynamically expand the size of the file. Mapping from logical to physical address in a file with a maximum, with a file. In a file with a maximum size of 256K bytes. And a block size, we only need 1 block. For index table. Right, okay, well, why 256K and not 512K? Cause each row is 2 bytes long? Okay, whatever, I don't know how long a pointer is, a pointer, let's say 2 bytes long, so then we could.
256
If we,
bytes.
if we had 256 rows, he's saying this, it's 256 row,
It's one by one.
oh, 1 byte
Byte.
long, sorry, it's 1 byte long, but 512 rows.
Meaning.
But each one is only a half a kilobyte, so this is only 250, so it's a half times 512, which is 256
Kilobytes.
kilobytes.
I think I understood.
The file size of 256 kilobytes requires how many blocks?
For the index table.
Assuming the block, no, just how many blocks, a simple question, I'm asking you. 256K file of blocks of 512 bytes. Well, if it would be blocks of 1024 bytes, then how many blocks would I need? 256. But it's half the size, so there are 512 bytes, so I need not 256 blocks, I need 512 blocks. You see what I'm saying? No?
I'm not sure.
A 512 size block is a half a K.
Okay.
If the maximum file size is 256K, how many half a Ks do I need to get there? Well, it'll be this times 2. Just math.
Yeah.
2 times 256. Again, this 512 is, just think of it as a half.
Okay, fine, okay.
That's a half of a K. And a half of a K, to get 256 of them, what do I have to multiply by a half to get 256?
2.
No, 512. 512 times a half is 256. A half of 512, what's a half of 512? 256.
Yeah, so why is the
Just
block?
check. How many blocks do you need, of 512 bytes do you need to fit in a file of 256K? That's the question. How many blocks do you need for it?
512.
Yeah, exactly, you need 512 blocks, so each block needs one row of the index table,
And
there's
it's
512 rows. If it's
Exactly.
nice in one block.
So if each pointer is 1 byte long, then.
Okay.
Then we need 1 block per index, and then our mapping would be like this, take the address that it wants, but wait a second. First of all, we know the beginning, so 9, so what are we gonna do with 9? 9 is the number we got.
No, 19 isn't.
No, we got the number 19, but we also got like, no, but we got like, no, we didn't get 19, we got like 513. We got 513, one byte number 513, where is it gonna be?
With start address 19.
We know the start address is exactly, it's 19, and we know that we want byte number 513, so where is it gonna be? So we're gonna do 513 divided by 512, we're gonna get 1 and 1 again. That's our favorite results. So our displacement into the index table is 1. So we go over here, and we go to index table, and we go 1, I guess.
16, no, it's not 0.
16. That's not seem right, that doesn't seem right, I like the 19. Oh, because, right, exactly, because the 19 is not used.
Yeah.
So we go to our table and we do 1, and we know it's 16. And then we get the 16, we also know it's 1, so it's 1 from the beginning of 16. So we got a logical address of 513, and we know where to go. We jump from 19 to here, and then we use our Q to tell us it's this row. And we use our remainder to tell us that it's this second byte in this file. It's very simple again. LA.
So you only need 1 block for the index.
Yeah.
You just use the next.
Well, that's what it's saying here. He's saying this, he tried to work that, he forced those assumptions upon you by saying. If the maximum file size is this, if the file size would be bigger, then we'd have to, then he didn't explain how we would do it. He
It'll
didn't
be,
explain how we would do it.
we're not gonna like. Split it into 2 blocks, and it's kind of complicated to jump between them.
I mean, yeah, exactly, you'd have to have 2 blocks, and then you'd have to say something like, again, some kind of special, like if there's no -1s here, we have to first check the last byte here and see if there's no -1. And if there's no -1,
Then it's a point.
then we know that this 9 here is actually pointing to another index table. And right, we could do it, but it starts getting, we then we couldn't draw a nice little picture like this. We couldn't draw a little division, it wouldn't be so simple. Because we would have to know, we'd have to take off 1 from it.
So I guess that's why you can't have anything bigger than 256.
Well, that's what he's saying, you could, anything is possible, again, we could do it, we just have to figure out a system for doing it.
And I guess that would be indexed allocation.
It would be a form of index allocation.
You know,
So-
linked index.
It would be a kind of linked list, right, it would be a kind of linked list, but it'd be a linked list, a limited size linked list, because it would only be for the table.
I mean, then hypothetically could add another link.
Yeah, keeps going forever. Okay, so wait a second, that's what that, mapping from logical to physical address in a file of unbounded length, that's exactly what we're talking about. Oh. Block size of 512, the link scheme. Link blocks of index table. Oh, like I just said, no limit on the side, we have link blocks of index table.
Index table.
We can also have multi-level indexing, and that's our INO. This is the Unix UFS, Unix file system. Isn't that a great name for
It's pretty
it?
Why is it, it's the Unix file system?
I think, or maybe it's not Unix file system, I think it's Unix file. You can look it up, maybe it's universal file,
Universal, it was like the other default word of the year.
it could be ugly file system,
I like that one.
maybe it's ugly file system.
I don't love the way it looks. We forgot the fat one.
Universal flash storage.
No, it's not this. That is not the right acronym, that
A
means
Unix file system, yeah, Unix.
What?
Unix file system, alright.
I like ugly file systems.
Unix files.
Unix file system, okay. So here is our inode. And I'm not saying whether there's a question on this, all these things are open game for the exam. Of course, we're going into. A bit, I mean, things that obviously that I'm figuring out as I'm telling them to you, probably are not on the exam. Because I didn't figure it out yet. But it could be, because I could say a question like, explain
I don't know how it
the
works.
index allocation.
I don't know.
And then you'll have to do it,
No,
correct?
I mean, more like, read this.
Yes, I don't know how it works, but please tell me. It's like, what if I don't figure it out for myself?
Like,
They interchange
please
it.
tell me how this works.
Yeah, they're changing and what we're doing now, exactly, the question I didn't say.
Please tell me how this works in parentheses.
And I really don't remember, there actually is a question on the subject matter, I don't remember what question.
I mean, if there wasn't, you probably would have stopped and not taught this class, it's my guess.
No,
But it's
wouldn't do that because I would be bluffing.
Oh, it's what?
Okay, let's see how far I wanna go.
So the inode is UFS, that's the inode?
So here, this is, I noticed the UFS, so,
Same.
so we have 4 K bytes per block, so not 512. Which is a half a K. We have 8 times bigger. Okay? 32-bit address, but each address is not 1 byte long like we were assuming there, but 4 bytes long. Each pointer takes up 4 bytes, so we're always limited. Okay? Now, what is in this inode? What we're calling an inode, could we ever call it an inode here? There's no real need to call it inode, but this is inode. File metadata. So just like other data about the file, maybe ownership, who owns it, whether it's a read-only file, you know, things like that. And then that's it. So that's all the metadata. Who's the owner, what the permissions are, is it read or write, whatever other data that might be, is not discussed here. Direct blocks. So these are just actual data. Everything blue here is data, is actual data. So there's the first,
Is it pointers?
in other words, just like we saw over here at 9.
Same.
Wait, I was saying, this 9 was 1 byte long, right?
Mhm.
And the next row was also 1 byte long, it's in 16. So if we would draw the same thing, we'd have the 9. The 9 would be over here in this gray area. And then the next one would be 16, and this blue block would be in the hard drive at location 9. And this block would be in the hard drive at location 16. In other words, the location is written over here and takes 4 bytes long. And that's the actual data. Wherever it is, that's the address of the data, and that's the actual data. So if and how, and we have a certain, here we're not getting into the details of how big it is. I think in the lab we said it's like, we did an example of exactly how many there were. But there's some number of direct addresses, and we could have done the whole thing as direct addresses. But then, when we got our file getting really large, we would run out of spaces. And then what would we do? We would do what I said, make a whole nother inode for it. And then, but instead of doing that, we did something simple. We do basically a similar thing, but it was a hierarchical system. We say it like this. We have, and then the next section is single indirect blocks, like we said in the lab. This will point to, well, what is this white thing?
That's a table.
White thing is a table of pointers. Well, how big is that? How big is that table? It doesn't say here, but what would be the straightforward answer?
2, 4.
No. Presumably an entire block.
Oh, yeah. That's-
Presumably that's an entire block. So it would be able to address a huge amount of references, right?
You have a 32-bit address.
This one would be a whole block. What else would this be? How are we allocating stuff? We're allocating by blocks.
Yes.
So it's presumably a block. This is a block address. What's in here is a block address. And that block address goes to this block. And that block,
No, it's more than that.
what?
32-bit is enough for more than a block. We said before that we've got the.
What's
the index.
32-bit?
Hmm?
Every address is 32 bits. So there's a row here of 32 bits. It points to a block. Here is the block. The block now has many rows of 32 bits, which each point to data. So I've already got a ton of data. Then I have a number of these pointers. Well, each one can point to null or -1 or to an actual address. And by the way, what's -1? Represented as in binary,
No.
all one, no, all ones.
Oh,
So we'll just have like, if it's all ones, then it means it's not, right? Now it's very easy to identify. So it'll point to another one, etc., etc. I mean, it could be, we could have 0 also. If it depends if it's two's complement or not, but if it, whatever, it doesn't matter. Probably it wouldn't be two's complement, because why would you want negative
Yeah.
numbers? And therefore probably it would just be
All
a
zero.
0. And 0 would be known to be invalid. Or it could be all ones is known to be invalid, doesn't matter. And it's some sort of number for invalid, for invalidity. Anyway, then, if we use up all of these direct, and this file is really large, now we have double indirect. So this will point to a number of, this is like one example, one block here. There could be another arrow pointing to one block. And then each of those will point to a block, and you see that we're gonna get huge sizes here, if each of these is a block. And if each of these is only 4 rows, then it won't be so big, but it'll still probably, but it could still be big enough to, I mean, eventually, we'd like it to be that this one inode can map a file, you know, of the biggest hard drive, you know, some, like a gigabyte, whatever, terabyte file, you know, something like that. So it might be that this,
So each of them are a block, how much can that? We could probably figure it out.
yeah, it's pretty big here. Well, we'd have to figure out how many of them there are. It doesn't say here in this picture.
No, we know it's, each one is 4K, it's 8 it's-
We know the size of this and we could, but we don't know how many are allocated here and how many here and how many, we don't know the division of rows.
I don't know.
And we don't know how big the metadata is.
There isn't just one for the single.
Well, here it says ... we don't know how many, and here it says, and here, I don't think it's just one, no, it says single indirect blocks. Oh,
Just one.
Single indirect block, no, it's multiple blocks.
no, these are the blocks.
Yeah.
These are the multiple blocks. You think it's just one pointer?
One pointer to one block that has.
Who says?
Uh,
Doesn't have to be like that. It could, I could imagine that these are many. You're right, they didn't draw ... But I could
So
just
they have
because
to
they have
go-
space. I'm not sure.
Should I read the paragraph in the textbook?
Yeah, what does it say?
To combine scheme, another alternative used in Unix-based file systems is to keep the first, say, 15 pointers of the index block in the files in node. First 12 of these pointers point to direct blocks.
Yeah, okay.
That is, they contain addresses of blocks that contain data of the file.
Right.
Thus, the data for small files of no more than 12 blocks do not need a separate index block. If the block size is 4 kilobytes, then up to 48 kilobytes of data can be accessed directly. The next 3 pointers point to indirect blocks.
So it's 3. There you go. Yes, that's all you need. I'm
And
right,
then soon it talks about single and then double and triple.
right. We got the idea.
So it's 3 blocks.
What's your name? I forgot your name.
Me?
Yeah.
Nathaniel.
Nathaniel, man, I keep asking you that. Nathaniel, so you hear the answer? The answer is it could be multiple. These are multiple.
Yeah.
So the next 3 pointers points to indirect blocks.
It says the next 3, for example, let's say, it's just an example. But the point is, it's not, it has to be, it doesn't have to be 1. As I was saying, it doesn't have to be 1. It just, in this picture, it's 1, but it doesn't have to be. Okay. Performance, method depends on the file, access type, continuous, great for sequential and random.
Let's go to the end, scroll to the beginning, you can. You don't have to like go through the whole link to find.
Link good for sequential, but not good for random. Contiguous is the best. Declared access type at creation, select either contiguous or link. You could do that, and as you could have both systems, and then you could have run both systems, and then you could have the files index more complex. Single block access could require 2 index block reads and then a data block read. Right, now you have to read several blocks just to get you to the data. The more jumps, right? Obviously, we prioritize these ones because these ones are going to require us to read another block and then get to the data. And these ones say another block and then another block and then the data. So it's much slower. So obviously, we're not going to start by putting stuff over here. That's the whole point. Only as the file gets larger, we'll have to have more jumps. So actually, it comes out that larger files are proportionally slower. Proportionally slower. Clustering can help improve throughput, reduce CPU overhead, right? If we refer to things as clusters, but of course we create fragmentation. For NVM, I don't know what that is, no disk head, so different algorithms and optimizations needed. Okay, skip that. I don't want NVMs.
I'm looking for,
All right,
No virtual memory.
Non-version.
Nice. Free space.
okay, I'm sticking it. File system, free space management, file system maintains a free space list to track available blocks clustered using the term block for simplicity. In other words, we're not gonna keep saying block clusters every time. Could be a block, could be a cluster, either way. So we have a bit vector, so we have a bit vector or bit map. Where it's the length at n, the number of blocks, we'll have a bit for each one, which will tell us what's free and what's not free.
The text here.
So, the text is not aligned, but basically you put a 1 in here and it means that the block is free and 0 means the block is occupied. We saw that before, it's in reverse, what you might think. And block number calculation, number of bits per word times the number of 0 value words plus offset of first 1 bit. What does it mean by block number calculation?
Like to figure out the next block number
Of what?
of like where's the next free space? I don't know why you count the number of 0 value words.
Oh. You know, what he's saying is like this, instead of counting everything that's a 0, now we're gonna understand a little bit why it's 0, I think. Because we can search for 0. The 0 means occupied, right? Let's assume that a lot of the disk is occupied. So all we'll do is we'll take a word. Let's say our word length is 32 bits. And we'll read the first word of this bitmap. If that word, its value is 0, then skip it, there's no blocks there. If it's anything other than 0, then there's gotta be a 1 in there, there's gotta be something free. So I can read, so let's say the whole disk is occupied except for a few places. So I can check blocks very fast, because I'll read 32 bits, which is 32 blocks, and I'll read that value in. If it's 0, next one. 32, if it's 0, next one. 32, if it's 0, next one. The minute I hit something that's not 0, I know I found a block. So that's what it's saying here. The number of bits per word, let's say 32. The number of 0 value words, let's say I have 10 in the beginning, I have 10 0 value words. So I'm gonna have to do plus offset of first 1 bit.
So
That's the number bit, that's the number block I want.
it's really the number of zero value words from the start.
Yeah, from the start. Number of bits, number of 0 value words from the start, exactly. You understand what I'm saying? Understand how that works?
Yeah.
CPUs have instructions to return offsets within a word of first 1 bit. CPUs have instructions to return offsets within a word of first 1 bit.
You gotta
In other words,
work with ones.
there'll be a special instruction in the CPU which will tell me where the first 1 is in this word. In other words, it'll give me back like 7 if it's the 7th one. And then I know 7. And I know that I did say my loop I read 25 words. So 25 words, so the number of 0 words was 25. And the size of it was 32, so 25 times 32 is 800. And then 800 plus the 7 that I got back from that CPU read, 807, that's my first block. You follow that? That's just the math. That's just why we do it as a 0, because if we would do it as a 1, then, well, I could still do it, I check for FF, I check for that value, and anything that's not FF,
Really
What
just
else?
find a 0.
but 0 is easier to check for in a sense.
I mean, look, if you search for a 0, just put it in there.
No, but we don't want to search every bit, that's the point. We don't want to search every bit, we want to search by words. It's like Moshe Feinstein, they once asked Moshe Feinstein, or it's a joke that I mentioned to you, but they had once asked Moshe Feinstein, and he would look at a tall building and say, that's a 96-story building. He says, how can you count so fast? Because he lived in Manhattan, so there was a tall building. And how do you count so fast? He says, well, I count by 10s. Counts fast. Did I say the joke about the shepherd?
Yeah.
yeah.
It's the opposite.
It's the opposite. It's the opposite. So Moshe Feinstein, now, this is a true story, this is written in his biography. He would, as for him, he would actually, for him, it was easy to count by 10, so he would just count by 10, he would just look and see, there's 10, 10, 10, 10, and he would just know it's a 90-story building. It's kind of like when you're at a wedding hall, you wanna see how many people are at this wedding hall, you see how many people sit at one table, and you count the number of tables. So we don't wanna actually count the number of bits, we wanna count groups of bits, so we're gonna count 32-bit words.
Okay, so you check the word, and if the word is zero.
Zero,
is
then
it-
then it's all occupied.
No, from what I understood
You
from
get to
the
the next
textbook is you have like a
And it's
block
not
where
zero,
each
then the other
bit
system
of it represents a block. And it's
Yeah.
just like, you know, like 0, 1, 1, 1, 0, 0, 0, and like
Yeah,
each
yeah.
zeros and.
Yeah.
But
But
not
imagine-
like go to each block, look at the first digit, then go to the next block, and look at the.
No,
first
I didn't
digit.
say that. I didn't say.
Right. Yeah, alright,
I appreciate that you're checking up on me, but
no, I was just trying, yeah.
no, yeah, exactly. You have one block which has the whole bitmap in it.
Yeah.
And in that bitmap, you read the first word, and if it's zero, if it's not zero, then you know then the first word you already found a free space. But if the first word is zero, go to the next word.
Right.
And now you count up how many times you have to read a word. And that
By
is
word.
the number of zero value words.
And by word.
And then the number of bits per word, well, you know your word is 32, so it's 32 times that. So that's what I said, 32, let's say you read, I said, what was my example, 25, you read 25 words. And then 32 bits per word, so you know 25 times 32 is 800. So, I think, yeah, 800, now 800 plus 7. If the seventh bit of that word is a 1, then it's 800, byte number 807 is the first free byte. And I did it by only having to read 25 words, I didn't have to read 800 bytes, 800 bits, like otherwise I'd have to read 807 bits, so I find finally one that's a 1. I don't wanna read by bits, I wanna read by words. Alright, I think we go to Minchel.
Oh, yeah.
Yeah.
That's interesting, I get why that would be the case, because they'll decide it differently.
They could have made it. They could have made it, you know, I explained it in the manual, that it could have been with ones, so we could have been reversed. And then instead of picking for a 0, we check for.